All right, let's talk about potential energy today, okay? So, there's various different forms of potential energy that exist out there, but they're all basically stored energy, okay? So any energy that is stored in some form. Now, there's various different types. The most common type is gravitational potential energy. Anything that has height has the potential to fall. So you're storing energy in height, essentially. So this eraser right here, if it's above the desk, it has some potential energy. Depending on where you point your reference frame, if it's on the desk, I would say there's no potential energy, but if you're measuring from the floor, there is potential energy of that eraser, okay? So anything that has height above the ground would have gravitational potential energy. Then you have elastic potential energy, which is, we've already talked about forces with springs, right? Elastic, in that spring, because it can apply a force if you distort it, it stores the energy, and when you let it go, it'll actually apply that energy. So the energy that's stored when you do stretch or compress a spring is called elastic potential energy. You also have chemical potential energy, which is the energy contained within the molecules of a substance. Think about burning a piece of wood. When you burn a piece of wood, what you're essentially doing is you're breaking the molecules between the molecules of the wood, and it releases heat and it releases light, and that's the fire that you see. But within the molecules, it stores energy. So then we've got the most powerful common form, which is nuclear potential energy. And nuclear potential energy is the energy contained within the nucleus of an atom. It's very powerful. And there are two processes that can release that type of energy. Process one is called fission, which happens in nuclear bombs and nuclear power plants. What it does is we take a uranium atom and we shoot a neutron into it. It splits it into barium and krypton. And then what you have is during that process, a huge amount of energy gets released. And so in nuclear power plants, we contain it and we control it. On bombs, it's just an uncontrolled form of that, okay? But it releases a huge amount of energy. The other form of nuclear potential energy that you see in the real world is fusion. And where does fusion happen? On the sun, right? We're taking hydrogen atoms, fusing them into helium, and during that process, it releases heat and light. So that is the energy that's contained within the nucleus. If we could do fusion, limitless clean energy. One day, you know. So there's two most common forms that we're going to quantify, that we're going to talk about mathematically. Number one is the gravitational potential energy, which is, the formula for that is PE equals mgh. It's measured in joules, and a joule, as we know, is a kilogram meter squared per second squared, okay? But if you forgot what a joule is, right, you could just put your units in here and it'll work itself out as to what a joule is. Mass is in kilograms, G is in meters per second squared, and height is in meters. When you combine all those into one unit, you get a kilogram times meter squared over second squared, which is equal to 1 joule. So, once again, we're consistent, because remember, the units for kinetic energy, joules. Work, joules. Potential energy, joules. Okay? Now, we talked about it depending on the frame of reference. Okay? So basically, it depends where you start. So technically, you might say that this calculator has no potential energy right now. Now, I might say it does. Neither of us are wrong or right. Okay? That right there has potential energy according to me, because I'm using the floor as a frame of reference, right? You might be using the table, and there's no correct answer. It's just you have to stay consistent, okay? So as of right now, it's on the desk, no potential energy. Or if you're measuring from the floor, yes, potential energy. That said, if I put something on the floor, like a calculator on the floor, what does it have potential energy now? could. Where would be the only place where there isn't potential energy?
Between the floor and the core.
The core of the Earth. Good job, okay? The core of the Earth. Because technically, could a chasm like open up right here and it fall into the ground? I know that's your dream, of course. Like, yes, a chasm opened up and Mr. Lingard plummeted to his death underneath there. But no, that's probably not going to happen. But theoretically, it could happen, okay? Score, exactly. Theoretically, it could happen, so we're measuring there. Now, we'll talk about elastic potential energy in a second, but first I want to show you this video, which talks a little bit about, potential energy in the center of the Earth, etc.
Commas in the wrong places. That can shift my credibility and ability to influence and persuade others.
So what if we did dig a hole all the way through the Earth, through the center, and jumped in?
Well, Michael, you probably wouldn't make it very far. That's because of the Coriolis effect, which is why a ball curves weirdly when you toss it while riding a merry-go-round, and why hurricanes always spin counterclockwise in the northern hemisphere. At the equator, the Earth, and you on it, is rotating eastwards at 1,600 kilometers per hour. As you go deeper, the bits of Earth around you are still spinning around once per day, but they don't have as far to travel, so they're going at slower and slower speeds. If you jumped into a vertical shaft, you'd soon be traveling east faster than the rock around you, so that after falling only a few kilometers, you'd crash into the eastern wall. It might not be a disaster, but some miners near Lake Superior tried to test this by dropping cannonballs down the mile-long shaft, and the balls never reached the bottom.
Okay, so what if the tunnel went from pole to pole so the Coriolis effect didn't apply? And let's also assume that there's no air resistance for friction.
Okay, since the Earth's mass is more concentrated close to the middle, gravity would actually pull you down with about the same amount of force for the first 3,000 kilometers. This familiar constant force would accelerate you until you were falling 8 kilometers every second, and the trip halfway to the middle of the Earth would only take 15 minutes. Soon after, you'd reach the Earth's outer core, and this is the point in your journey where the pull of gravity would be strongest, but only slightly stronger than the force we're used to on the surface. As you continue to fall closer to the center, so much of the Earth's mass would now be above you that it would begin to seriously cancel out the attraction of the mass below, and the downward pull would weaken until you reach the center. Here, you'd experience no gravitational pull at all, or rather, the Earth would be pulling on you the same amount in all directions.
No potential energy.
Or freely around with no sense of up or down. Except remember that you'd be speeding past at 22,000 miles per hour, or 6 miles a second. Once you pass the center, the whole process would reverse, and you'd gradually slow, pulled down, or is it up? Weakly at first, and then more strongly, until when you got to the other side, you'd stop moving and could step out on the surface, a mere 37 minutes, or one dryer cycle later.
Of course, the deepest we've ever been able to dig is the Kola super deep borehole in Russia, but it only went down 12 kilometers, which is only 2/3 the length of Manhattan. They had to stop because it got too hot, 180 degrees Celsius. And this is sort of the problem with digging a hole through Earth. Earth is hot and molten in the middle. You can't just dig a hole through it with shovels. But here's a question. What if the middle of Earth wasn't all liquidy? What if Earth was hollow?
All right.
Weighed the same.
That's where he kind of gets a little off topic. He always seems to do that. No, we're okay. So let's quickly talk about elastic potential energy, okay? So elastic potential energy is the energy contained within a stretched or compressed spring. And the formula for that is 1/2 kx squared. What does it kind of look like? Well, I mean, what does the 1/2 kx squared look like? It looks like the kinetic energy formula a little bit, right? So the K here is the spring constant. It's actually measured in newtons per meter. X is the displacement from the resting length, which is in meters. Now this is the tricky part about this formula, is the X is the distance, displacement from resting length. So what does that really mean? What if I had a 3 meter long or a 2 meter long spring, right? And then I stretched that 2 meter long spring to, we'll say, 5 meters. And I'm just making up numbers here, okay? Now, X would not be the 2 meters. X would not be the 5 meters. X would be 3 meters. So it's the difference between stretched and compressed lengths, which is going to be measured in meters. And ironically enough, if you put the units in, you'll notice that it's a newton per meter. and then meter squared over here, which ends up being a Newton meter, which we know is equal to a joule. So we're back to joules again, which is good. Okay? Now, I would like to do a few of these we do problems with you guys. So if you guys could get out your we do sheets, we'll do those.